In this video, we're going to take a look at three-dimensional coordinates and then vectors in three-dimensional coordinates. So vectors in space and space coordinates. So there'll be, instead of just two number lines, the x and y axis, we'll have three number lines. The x, y, and z axis typically are the variables that are used. So first, let's start with a three-dimensional coordinate system. So instead of just having the x and y axis meet at a right angle, we're going to have a third axis, typically called the z-axis, perpendicular to both of those, so both the x and y axis. So the way that I'll typically draw this is I'll have the x-y axis kind of laying flat like a table, and the z-axis will be going up through that table. So I'll have the positive x-axis kind of coming towards us, positive y-axis headed to the right, and the positive z-axis headed up. It's three-dimensional though, so you can kind of rotate this and draw this however you want. That's just going to be my standard go-to way of drawing this three-dimensional coordinate system. Instead of having ordered pairs, we're going to have ordered triples, x, y, and z. So there'll be a third number in our parentheses, where x is the directed distance from the yz plane. So you've got the z-axis and the y-axis. So for us, that would kind of be, the way I've drawn this, it'd be kind of like a vertical wall. And then the x-coordinate tells you whether you are so many units in the positive direction away from that vertical wall, or so many units in the negative direction away from that plane, the yz plane. So notice we only have arrows on the positive part of the axes, because since these can be drawn in a lot of different ways, your audience always needs to know which way is positive. So we put arrows only on the positive ends of the axes. Well, the y-coordinate would be the directed distance from the xz plane. So z is right here, x is right here. So the xz plane would be the two-dimensional plane that contains both of those axes, and the y-coordinate will tell you how far to the right of that plane or left of that plane you are, the way I've drawn it. So positive direction, negative direction. Z is the directed distance from the xy plane. So the way I've drawn it, xy plane is kind of like a table. So a positive z value means you're above that table, and a negative z value means you're below that table in the way that I've drawn this. So for example, if you were to plot the point -2, 3, 3, then you would need to go -2 in the x direction, so -2 in the x direction. Then you would go 3 units in the positive y direction, which I've shown right here with this dotted segment, and then 3 units in the positive z direction, so you're above that 3 units. So it's hard to draw these and picture it in 2 dimensions, so whenever I can, I'll try to provide a 3-dimensional picture using software for you. So let's take a look at the first one of those, just to give you an idea of what these points look like and how it really is in 3 dimensions. So we'll go ahead and open up GeoGebra here, and let's see what we got. So I've got this point plotted, 5, 6, 2. So that's 5 in the positive x direction, so there's the arrow. That is 6 in the positive y direction, so we go 5, 6 this way, and then 2 units up, because it's 2 for the z-coordinate. So notice I've got the xy plane drawn here and kind of shaded gray, just to kind of give you an idea where that's at. And then since z is 2, we're above that 2 units. So as you can see, we are above that. We are up 2 units on the z-axis there. And then again, you can draw this however you want. So typically we need kind of a standard way of drawing it. So I usually will draw the x, y, and z-axis so that x is right here, positive y is here, and positive z is here. Now notice if z is negative, it'll be below the xy plane. So see how z is -2, and it's below the xy plane. So z is controlling whether we're above or below the xy plane in the way the fashion that I draw these typically. Okay, We'll do some graphing in 3 dimensions, but not a lot, since it's hard to do on a piece of paper. Well, in 3 dimensions, we need a distance formula. So it turns out the distance between 2 ordered triples is just an extension of the 2-dimensional distance formula. So you're just going to subtract the x coordinates between the 2 points, square it, subtract the y coordinates, square them, subtract the z coordinates, square them, add them all up, and find the principal square root. So it's exactly the same as this 2 dimensions, just we now have the difference of the z values being squared. And midpoint, we need a midpoint formula. So if you have a line segment and you want the midpoint of it, you just find the average of the x coordinates, average of the y coordinates, and average of the z coordinates. So it's just an extension of the midpoint formula in 2 dimensions. And then also say we need a sphere in 3 dimensions. So a circle in 2 dimensions, sphere with 3 dimensions. So let's say its center is x naught, y naught, z naught, and its radius is r. Again, it's just an extension of the formula in 2 dimensions. So you do x minus the x coordinate of the center, square it, plus y minus the y coordinate of the center, and square it, plus z minus the z coordinate of the center, and square it, and that'll always equal the radius squared. So remember, the formula for a circle is related to the distance formula in 2 dimensions. So that's why we bring up the formula for a sphere right now, because it's related to the distance formula for 3 dimensions. So if you were to square both sides, you would just get the formula for the sphere. Okay, so just to work a little bit with that, let's find the equation of the sphere that has 5, -2, 3, and 0, 4, -3 as the endpoints of one of its diameters. So the diameter is the line segment that contains the center, and the center would be the midpoint of that segment. So the center, we're just going to find the midpoint of the endpoints of the diameter. So that'd be 5 plus 0 squared, and then 4 plus -2 squared, or 4 plus -2 divided by 2, sorry. And then -3 plus 3 divided by 2. And let's see what we get. We get 5 halves. Let's see, that's going to be 2 divided by 2 is 1. And 0. So 5 halves, 1, 0. And the radius would be the distance from the center to one of the endpoints. So the radius would just be the distance. Let's say we take the center and let's do this endpoint here. So it'd be 5 halves minus 0 squared, 1 minus 4 squared, and 0 minus -3 squared. And that comes out to be principal square root of 97 over 2. So that would be x minus 5 halves squared plus y minus 1 squared plus z squared equals 97/4. So that would be the equation for the sphere with those coordinates as the endpoints of one of its diameters. So again, let's see a picture of this in 3 dimensions, just to kind of get an idea, mental picture how this is all. Okay, so let's take a look at that sphere in 3 dimensions, just kind of get an idea of what that would look like. So notice I've got our sphere equation up here, 24.25, that is 97/4. So the radius is about 4.92 units in length. So there's our center. You go 2.5 in the positive x direction, 1 in the positive y direction, and then 0, so you don't go above or below the xy plane. And so you see our sphere here in red. So it dips above and below the xy plane, and then we've got our radius of 4.92. I've got just kind of a generic point plotted on the edge of that sphere. So if we move that point anywhere, notice the radius doesn't change, still 4.92. So there's our sphere in 3 dimensions. Okay, so how about vectors in 3-dimensional space? Well, not much changes. So component form, you'll just have a third component, v3. So it'll be v1, comma v2, comma v3. So component form, remember the initial position will be the origin, so it'll start at 0, 0, 0, and then v1, v2, v3 will be where it terminates. The 0 vector will just have a third coordinate, so it'll be 0, 0, 0, still denoted 0 with an arrow above it. The unit vectors, I, instead of being 1, 0, it's going to be 1, 0, 0. J is going to be 0, 1, 0. And then we're going to have a third one, K. It'll be 0, 0, 1. So it'll run 1 unit up the z-axis. So the I runs 1 unit along the x-axis, J runs 1 unit along the y, and K runs 1 unit along the z. So if we do a linear combination, it'll just have a third term here with K, the unit vector K. So our v3 will just be paired with K. Length doesn't really change much. It's still the principal square root of, since the distance formula really didn't change much, it just added that third part that looks just like the other two. It'll just be v1 squared plus v2 squared plus v3 squared, with the principal square root of that. And then if you want a unit vector in the same direction as some given vector, we still, again, same basic idea, we just have this third component. So you do the vector in component form divided by its length, as long as its length isn't 0. To add two vectors in 3-dimensional space, you just add their components, and scalar multiplication in 3 dimensions, you just multiply each component by the scalar c. So no surprises here. Alright, so let's practice with that. So let's find the component form of vector v, which begins at -2, 3, 1, and terminates at 0, -4, 4. So remember, a vector is a representative of every single directed line segment that's equivalent to some given one. So we've got this given directed line segment, -2, 3, 1, that terminates at 0, -4, 4. So vector v is going to represent all of the directed line segments equivalent to this one. Well, let's write vector v in component form. So vector v in component form, we're going to go 0 minus -2, and we're going to do -4 minus 3, and then 4 minus 1. And that's going to come out to be, let's see, 2, -7, 3. So we're going to refer to this vector as the one that starts at 0, 0, 0, and then terminates at 2, -7, 3. So there's its component form. Then we need to find a unit vector in the direction of that. So this vector does not have a length 1. So let's find a unit vector that's in the same direction as this one. So let's find the length of this vector v. So it'd be 2 squared plus -7 squared plus 3 squared, which comes out to be principal square root of 62. So our unit vector in the same direction as v will be 1 over principal square root of 62 times vector v. So there's some scalar multiplication here. So we're going to end up with 2 over that principal square root, -7 over that principal square root, and 3 divided by that principal square root. So again, let's take a look at this in 3 dimensions, just kind of get a feel for what's going on here. So we had this vector that started from 0, 0, 0, went to 2, -7, 3, and we now created a vector with a length of 1 that's in the same exact direction as that vector v. So let's take a look. So the vector as it was given to us started at -2, 3, 1, and then terminated at 0, -4, 4. So that was as it was given to us. Then we moved it to have an initial point at 0, 0, 0, but it needed to be the same length and in the same direction, so now it terminates at 2, negative 7, 3. So that is the directed line segment we're using to represent all of the directed line segments that have that length and are in that direction. So you can see that they appear to have the same length and are in the same direction. You get an idea of what they look like here. And then we created a unit vector that's in the exact same direction but a length of 1. And if you look closely, I've got that graphed right here. So it starts at 0, 0, 0, runs right along our vector v, but will have a length of 1. So if you were to rotate that down along, say, the green axis here, that'd be a length of 1. So I just had the software plot all of those, so you can kind of get an idea of what we did. We took this given directed line segment, moved it to have an initial point at 0, 0, 0, and then created this unit vector u that's in the same direction as our vector v. Okay, so what do we mean by parallel vectors? Parallel vectors. So we're going to say that two non-zero vectors, v and u, are parallel if one of them is a scalar multiple of the other. So if, let's say, vector u is a scalar multiple of v, then we're going to say they're parallel. So all we need is one of them to be a scalar multiple of the other, and then we're going to say that they're parallel. So parallel in this case doesn't mean what it did in Euclidean geometry where they never intersected. That's not necessarily what we mean, but there's some similarities which I'll show you here in a second. So for example, say vector w has an initial point of 2, negative 1, 3, and terminates at negative 4, 7, 5. Which of the following, I give us 2 here, which of the following vectors is parallel to vector w? Well, let's find out. So let's check this first one, vector u. So let's switch vector w to component form. So that would be negative 4 minus 2, 7 minus negative 1, and 5 minus 3. So vector w in component form would be negative 6, 8, 2. Well, vector u, so u, which is 3, negative 4, negative 1, is simply vector w multiplied by negative 1/2. Because that would be positive 3, that would be negative 4, and that would be negative 1. So vector u and vector w are parallel. Because one is a scalar multiple of the other. Let's look at vector v. Well, for them to be parallel, we would need some scalar c such that 12 would have to be c times negative 6, because negative 6 is the first component of w. Negative 16 would have to be c times 8. And then 4 would have to be c times 2. Well, this would imply that c has to be negative 2. This would have to imply that c is negative 2, but this would have to imply that c is 2. Well, so there is no one c value that, when multiplied by the other one, would result. So like if we took v and we try to multiply by the same number, c, each time, we would not end up with negative 6, 8, and 2. So they are not parallel. Okay, so let's take a look at that using some software here. See what we mean by a parallel. So again, we found that vector W and U were parallel, but W and V were not. Alright, so let's take a look, see what we got here. So, what I've got plotted for us here, I've got W before it was moved to have an initial point at the origin. So it was starting at 2, negative 1, 3, terminating at negative 4, 7, 5. But then we moved it to have an initial position at 0, 0, 0. So then its component form was negative 6, 8, 2. So that's the one I've got called W here. Notice it starts at 0, 0, 0. Well, then I went ahead and plotted V, vector V. So here's vector V. And I also had to plot vector U. So now we can kind of get an idea of why one's parallel, one's not, and what we mean by parallel. So notice that vector U falls along the same exact line as W after it's been moved to have an initial point at 0, 0, 0. So it's sharing the same initial point. Notice they fall along the same line. Not only that, notice that vector U would not intersect W, the equivalent directed line segment for W that didn't start at 0, 0, 0. So in that sense, they'll never intersect. So that's kind of where the never intersect thing comes in. But remember, we have all these equivalent directed line segments, and then we have a vector that stands for all of them. So when they all start at 0, 0, 0, notice they fall along the same line. But notice V does not fall along the same line whatsoever. And V was not parallel, whereas U was. So really, at the end of the day, we just need them to be scalar multiples of each other. It doesn't so much have anything to do with never intersecting. It gets a little tricky if we try to think of it that way.